All right, so let's talk about our different subatomic particles. Subatomic. What's that sound like, Fred? What's subatomic mean?
Subatomic? Like below the atom?
Below the atom. That's right, or smaller than the atom, right? We're talking about atoms that are, or sorry, particles which are smaller than the atom. Do you have any idea what they are?
Um, Protons, neutrons, and electrons.
Very good. Protons, neutrons, and electrons. These are our three subatomic particles. Okay? And as we've mentioned before, the protons and neutrons are in our nucleus, and electrons are on the outside, right? Here are the masses of these different entities. Notice how the mass of the proton and neutron are very similar, but the mass of the electron and proton, or electron and neutron, are significantly different. Which one's smaller, Fred? Can you tell there by looking at those two?
Um, Negative 28 and negative 24. I'm not sure what that means.
Okay, so look at this. This is scientific notation, right? It's saying 9.1 times 10 to the minus 28. Now, do you remember what that means?
Not really.
It means that the 28 is how many times you move the decimal point to the, and the negative sign here means to the left. So this is 0.00000, 27 zeros, and then 910,939 grams for every electron. Okay, so which one of these numbers is smaller, the minus 28 or the minus 24?
The minus 28.
That's right, the minus 28 is smaller. So protons are larger than electrons, as neutrons are larger than electrons as well. How many times larger, can you tell?
I guess I could put in my calculator.
Do you know how to put those numbers into your calculator?
I think I do.
All right, so some of you have different kinds of calculators, and putting scientific notation into your calculators is different. Many of you will have a TI like this one, and if you don't have a calculator, it's time to get a calculator. You need to have a calculator. Don't borrow, don't rent, buy your own. It's a really small investment relative to how much time it'll save you and how much improvement it'll allow you to have on your grades and understanding, and that's going to result in a lot better position, a job for you in the future. So please get yourself a calculator. Now, if this isn't the one, I'm going to teach you how to use scientific notation on here, but on YouTube there will be somebody teaching you how to use scientific notation for your specific calculator. So you can do that if you need to. But if I want to write this in, 9.1 times 10 to the minus 28, there's a variety of ways that people try to do it, but there's one way that is important to do, because if you do it this way, then the calculator won't be confused later on when you start dealing with significant order of operations, right? So this is how I write that in. I'm going to write 9.1, right? And then I go times 10 to the, so that goes second, and then this little comma down here, times 10 to the, and then I just put in the negative, in this case, this negative sign here, 28. All right. Whoops, didn't put in 28, so go back a little bit. 28, there we go. So that's 9.1 times 10 to the minus 28. Okay, so I'm going to put in now the mass of the proton, 1.7, I'll round it to, times 10 to the minus 24. Okay, and now I'm going to take that number and I'm going to divide it by this number up here, and then I'm going to push enter, and we see that the mass of the electron is about more than 1,800 times smaller than the mass of the proton. You see that?
Yeah, I see that.
Okay, so what that's telling us is, well, I mean, it's just relative mass, and it's important to recognize. It's important to recognize. It's important to show that the mass of an atom is due to its protons and neutrons, and its electrons generally are not going to give a significant contribution because it takes that many of them to give you the mass of a single proton. Okay? Good. So, our charges, electrons have negative charges, protons have positive charges, neutrons have neutral charges. All right, so why do elements or atoms differ from one another? It's because of the number of protons that they have. All right, so hydrogen has 1 proton, carbon has 6 protons. Sometimes you'll see this number written down to the bottom left of the elemental symbol like that, and that's the way of telling you how many protons there are. It's kind of redundant because in the periodic table, um, we can also identify the number of protons very easily. So if we know what element it is, hydrogen, then we know that it has to have 1 proton. Carbon has to have 6 protons. So if I have my periodic table here, I can see hydrogen. Hydrogen's right here, right? And that 1 right there tells me the number of electrons that, number of protons that the hydrogen has. It also actually does tell me the number of hydrogen or electrons the atom would have if it was neutrally charged. Okay, and again, here's carbon. Carbon has 6 protons, and that's that number telling us there's 6 protons, right?
Okay, I got it.
All right, here's chlorine, Fred. How many protons does chlorine have?
It has, is that a 17?
That's right, 17 protons. Very good. So that number, called the atomic number, is telling us how many protons there are. And if it's going to be shown symbolically on when somebody's writing, it's going to be the bottom left subscript like that. All right. The mass of an atom is the sum of the protons and neutrons. And that number is written at the top like this here. So carbon, and we call it carbon and the mass number, which is carbon 12 in this case. Carbon 12 has 12 nucleons. Now that's a different word. It's not protons and neutrons. It's what's in the nucleus, which is the sum of the protons and neutrons, right? So carbon 12 has 12 nucleons. You know how many protons carbon has?
Protons?
Yeah.
Carbon?
Yeah, how many protons does carbon have?
Well, that's just the 6, right?
That's right. 6 is here. And again, we could have brought in our periodic table. And again, looked at the carbon and seen that number right there, 6, right? That's the number of protons. Okay, so carbon 12 has 6 protons and 6 neutrons because, again, that 12 up there on the carbon 12 is the sum of the protons plus neutrons. This down here is just the number of protons. Okay, good. Carbon 13, Fred, how many protons and how many neutrons?
Carbon 13?
Yeah.
What's the 13 again?
13 is the mass number. It's the sum of the protons and neutrons. And we call it carbon 13 when it's, that's the way we identify the number of protons and neutrons, the number of nucleons in the atom. We say the number afterwards, like carbon 12 or carbon 13. So carbon 13, how many protons and how many neutrons?
Does it have more protons or neutrons?
You mean compared to carbon 12?
Yeah.
Well, it can't have more protons because if it has more protons, it would be a different element. If it had 7 protons, what would the element be?
I don't know.
Well, yeah, we could look on our periodic table and see, 7 protons, that's nitrogen. Nitrogen must be the one that has 7 protons. So if you increase the number of protons, you get a different atom. But if you have the same number of protons and a different number of neutrons, 2 atoms that have the same number of protons, different number of neutrons are called isotopes. Isotopes. That's what we call elements that have atoms that have the same number of protons but different number of neutrons. They're chemically very, very similar, but they do have slightly different properties. Well, they have different properties physically. They undergo nuclear reactions, but at different rates. But we're not going to talk about that for quite a while now. Okay? So, the atomic notation is with our elemental symbol, our atomic number, and then our mass number. All right? So here's a problem for you. If I have this element, what is this element?
Is that carbon, I don't know,
CO, we can look on our periodic table. We can bring up our periodic table, find CO. Here it is. And CO is for cobalt. So if I have cobalt right there, I can call it cobalt 60 because the mass number is 60. If I have cobalt 60, can you identify the number of protons, neutrons, and electrons in cobalt 60?
How would I do that?
Well, 60 is our mass number. We look down here, we can identify the number of protons. The 60 minus the number of protons must be the neutrons. And then the electrons, again, are the same as the number of protons when we don't have a charge on our atom. And on these atoms here, there's no charge. Okay? All right, I'm going to give you guys a second to try to figure it out. Push pause. Try to fill in these blanks here, and then we're ready to go again. All right. So, did you get these values?
Yeah, I did. 27 protons and 27 electrons. You said because it doesn't have a charge, protons is the same as electrons, right?
That's right. Good job. All right, bromine 81.
That's what I got.
All right, excellent. So what's this last one here?
Oh, that's copper 65.
Very good. Copper 65 is what we call it. 65 nucleons, mass number, sum of the protons and neutrons. And then electrons, again, is the same as the protons if there's no charge.
How would you know if there's a charge?
Well, if there's a charge, for example, if I have bromine with a charge on it, and it could be a positive charge or a negative charge, but that would show up right there. So if I had bromine 81 with a negative charge, that negative charge would show up right there. And that negative charge means that there's more negative charge around this species, and that is from electrons. So for every negative charge, I have one more electron than I do on the neutral, the uncharged species. All right, we'll talk more about that as we get on here. Okay, good place to stop. All right, here's a practice problem for you. An atom of lead 206 has this many protons, neutrons, and electrons. All right, can you work on this one?
Yeah, I think I got it.
Push pause, work on it if you haven't got it yet. Okay, what's the answer, Fred?
I think it has to have 82 protons and 82 electrons, so I think it has to be D.
Very good. It has to have the same number of protons and electrons because there's no charge on it. And 124 plus 82 is our 206. Okay, how about this one? How many neutrons are there in iron 52?
I think the answer.
Hold on just a second. Let them work on it at home. Okay, push pause, work on it, find your answer. Welcome back. Did you get it?
Yeah, I think the answer is C.
All right, very good. 26. Now, there happens to be the same number of protons, that's what that 26 here says here, as neutrons, and that's not uncommon. 26 protons, 26 neutrons gives us our mass number of 52. So what we did here is to find the neutrons. We took our 52 and we subtracted the number of protons. All right, so an element like chlorine exists in nature, and when we say exists in nature, we can say naturally exists or naturally occurs. It exists in nature as two isotopes, two major isotopes, chlorine 35 and chlorine 37. All right. Chlorine 35 has a mass of almost 35, 34.9689, and chlorine 37 has a mass of 36.9659. So what we want to know is what is the average atomic mass of chlorine? Okay. What do you think? How would we solve this one?
The average, just add the two together and divide by 2.
All right, add what two together?
34.9689 and 36.9678, or 59.
Very good. Well, I mean, that's not right, but that's how you do take the average. You would add this value to this value and divide by 2, and that would give you the average. Now, why can't you just take the average here?
Well, I don't know. Why can't you?
Well, it's because not half of I don't just have two atoms. If I did just have two atoms, one with a mass of 37 and one with a mass of 35, then I could add them together and divide by 2. That would be the correct way to approach this problem. But here, I have different percentages of the different masses. So think of it this way. If I have a hat, and I have inside this hat 100 different atoms of chlorine, and they differ in their masses. Some are chlorine 35 and some are chlorine 37, and I want to know the average. How would I find the average of all the different atoms of chlorine in this hat?
Just take them out, find their masses, and add them all together and divide by how many you have.
Okay, that's right. That's right. And let's say I take out 10,000 atoms. All right, 10,000. And let's say that as I'm pulling them out, I'm writing down the masses that there are. So instead of writing down the masses, I'm going to use a tally mark. So I'm going to say how many of them have the mass of 34.9689 and how many have the mass of 36.9659. Okay, so I'm going to be taking the tally for both of those. Okay, so I pull the first one out and it has a mass of the 34.9689. So I'm going to put 1 there. Pull the second one out, it has the same. Third one, same. Fourth one, now it's this mass, it's the 36.9659. I pull out the next one, okay, it's this mass, the next one, this mass, the next one, that mass, all right? So how would I find the average if I stop right here and I had 7 atoms pulled out of the hat? How would I find the average?
I'm not sure.
Well, I would take the 34.9689, multiply it by 7, because that's how many of those I had. I would take the 36.9659, multiply it by 2, right? So that's an easy way of adding up all the values that I have. And then I would take the sum of all those and divide it by how many I pulled, which is 7, and that would be my average. Does that make sense? So I would do 34.9689 times 5. And then here I would go 36.9659 times 2. So I could take this sum and add it to this sum there, and I have the overall sum. And if I divide that by 7, it says my mass average is 35.53. That's the average of the 7 measurements that I've made so far. Now, just doing 7 is not very much, so I'm going to do it over and over and over again until I get lots of tally marks on both sides, right? And in fact, that's what this experiment is saying. It says they had a number of atoms and they looked at them and they saw that 7,577 of the 10,000 atoms had a mass of the chlorine 35 and 2,423 had the mass of the chlorine 37. Okay? So now I can take this, multiply it by the mass there, and this and multiply it by the mass there, and divide them both by, how many did I pull out altogether?
Well, I'm lost. I don't understand what's going on.
Okay, so I have a hat here, and I have 10,000 atoms inside it. And I pulled out all the atoms. This plus that equals 10,000. And this many of them had that mass, and this many of them had that mass. And now I want to find the average mass. And notice that it's not just adding these two together and dividing by 2. The way I find the average mass is take how many of this there were times that, plus how many of this there were times that. So this times the 34.9689 plus this, how many of them had that mass, times the 36.9659 divided by my 10,000. Okay? And that is going to be the average mass. Now notice, I could have done it like this, 75.77 and 25.23, which are the percentages. Percentage means for every 100, per century. So this is per 10,000 down here. But this problem here is just out of the 100 percentage. So if I take the percentages times their masses, then divide by 100, I can also get the average mass. All right. Now, this average mass is actually what's appearing when we look at the periodic table. So if we look at chlorine, for example, chlorine, how many protons does an atom of chlorine have?
17.
That's right, the 17 there. What is this number, the 38.48 or 4527? Any ideas? Not 38, 35.4527.
Oh yeah. That's, is that the, I don't know, what is that?
Well, it's just what we found, isn't it?
Oh yeah.
It's the average mass of a chlorine atom. Okay? So it has this fraction number. It's not a whole number always because of the different isotopes that exist, right? Again, this is an isotope, chlorine 35, and chlorine 37 is a different isotope. So the numbers that we see on the periodic table here, let me see if I can zoom in a little bit. There we go. Can't zoom in. So that number there is what we call the average. It's the average mass of a chlorine atom, of a naturally occurring chlorine atom. So the average mass of a naturally occurring hydrogen atom is 1.0079, titanium 47.88, and so forth. Okay, good job. We're going to need to know that, so remember that.